continue from previous video where we found the structure analysis for finding the shear and serviceability of the steel beams. Now we are going to move on to the third steps where we want to check the bending capacity of the steel beams. Generally the beams governed by the bending capacity. The shear check comes after the bending, so we always do the bending check first. If you're designing for shear steel, we require to do the bending check, making sure that the beam does not fail in the bending rather than shear. So the shear comes after, and generally beam generally don't fail in the shear, but we must check for the shear. Now for flexure bending strength, you're going to use the 300 grade, and the beam is continuously restrained by the reinforced concrete slabs. So we are in the questions, it has saying that beam is attached to this steel beam. So you can say that beam is attached to this steel beam. So this flange will not have any deflections, lateral deflections or rotation, is fully restrained. So as in the previous video we said that if the steel beam is fully restrained, this steel beam is governed by the section moment capacity, not the member moment capacity. So we're going to find the section moment capacity for fully braced steel beam. So this condition is given in the Australian standard in the on the page number 49 on AS 4100. We have given the design for bending moments, and we have given for the sections MSX star less than or equal to 5 MSX. So this one is coming from the bending moment diagram, and this is design moment for the particular beam. So that's what written here. And then we have this 0.9 FYZE for the MSX. If you turn the page over, they have provided the equation on page number 50. So we have a nominal section capacity MS, and we multiply by safety factor, that is FYZE. Now that's FYZE, and this 213 times 10 to the power 6 that we calculated from the structure analysis. As I mentioned, this is the M star, 213 kilonewton meter. So that is design capacity. So this capacity always greater than what we obtaining from the bending moments. Now this unit I converted times by 10 to the power 6 because here the unit was kilonewton meter. So multiply by 1000 and multiply by thousands 2 times to convert into Newton millimeters. And we have a 0.9 FYZE. We need to interested in find this effective section modulus ZEX greater than or equal to 213 times 10 to the power 6 divided by 0.9, and Fy is 300 megapascal. So we are selected these steel beams, which is 310 UB 50.40.4, and we say that is the grade 300. So if you turn it over, 310 UB 40.4, we have this 320 megapascals, but we are taking 300 megapascals because we mentioned this grade 300. So ZEX, the calculation give 855 times 10 to the power 3 millimeter cube. Now we going to check in the Australian standard. We going to check in the one steel table, and we are targeting to find the ZE value which is greater than 855. So if you go here, 310 UB 40.4, it has a SX value which is 633. Now we need 855, so we need to go to 360. We need to go here 360 50.7. So we are selecting 360 50.7, and SX value is 897. So that's what we are selecting, 897 times 10 to the power 3, that is greater than 855. So now the trial section is 360 UB 50.7. that has a section modulus more than 855, which is 897, that is taken from one steel tables. Now design for shears, we need to do the checking for the failure, whether it's failed by yielding or whether it's going to fail by buckling. So that's the design of the section. If you take these steel beams, that will satisfy the bending capacities, right? So therefore this check has done for a bending one. Now as I mentioned, we need to check yielding or buckling. How do we know? How do we check? So there is a clause 5.11.2 on page number 68. It has two equations. First is for yielding and another one for buckling. On AS 4100 on page number 68, we have clause 5.11.2, we have dp on tw less than or equal to 82, that's square root, and that's used for checking the checking this yielding. And on the next page we have this dp tw greater than 82 on page number 69. It is used for checking the buckling. Alright, so we're going to make two checks. We're going to find these values and find this value, compare these two, and we will find which condition is correct for this particular case. Now left hand side, which is this one, dp, depth of the flange, that is here, divided by tw, so 356 take away. So if you're checking this this from the one steel tables, and we have 360 ub 50.7 that we just selected from this. We selected this 360 ub 50.7. For this case we are going to find a dp value and tw. So 360 ub 50.7. now the dp value that we going to find is the depth between the flange, which is 356, which is the depth of the hole take away. So that is 356 is here, that is 356, and we're going to take away these two, which is 11.5. that will give us the a dp. So we take away this flange width, which is 11.5, 360 ub, and that is 11.5. These values, which is 46, also given in the one steel table, so you no need to calculate that one. If you go across here, that is 45.6, that is dp on tw, that is given here 45.6. so we can take straight away from here, that's value straight away from the one steel table, so you no need to calculate this one, it's given in this one. So it's basically this length divided by this tw, 7.3 flange of the web. And right hand side is 82 divided by fy on 250s, and we taken 300 grade, so 300 megapascal on 252, 82, that is 72. So please compare this value. 46 is less than 72. So comparing here, 46 is less than 72. So the beam is failed by yielding in the shear. So left hand side is right, then web will fail by yielding. Now for yieldings, we have a equation to calculate the shear capacity. Vu is equal to Vw. That where is coming from? That is coming from the Australian standard. That in the page number 68, we have a nominal shear capacity. Vu is equal to Vw, because we have this yielding failure. Now in that yielding failures, we have Vw that we need to find. Now that Vw is given on the clause 5.11.4 on page number 69. In here, page number 69, we have given the nominal shear yield capacity of a web, that is Vw is 0.6 times Fy times Aw, and Aw is the gross cross section area of the web. So Aw is just this area for the web. So 0.6 times Fy times 300, so that distance is 300. Is also given in the one steel tables, 360 50.7, and that is 300 here, times 7.3. thickness of the web is 7.3 here, thickness of the web 7.3. so that is all the notation is given here. So that is the area Aw, and Fy is 300, that give us 437,562 newtons. And then Vu is equal to Vw, that is 437 kilonewtons, that we just calculated here. 437 divided by 1000 give us 437 kilonewtons, and multiply by the safety factor phi Vu, that is give us 0.9 times 437 gives 394 kilonewtons. Now we're going to do the check. Shear, that is coming from shear force diagram, that is the design shear force, should be less than 5 Vu that we calculated. Now from this 154, that is we calculated at the start, In structure analysis, we calculated this 154 kilonewton, that's design shear force, that is 154, and 5 VU is 394, that we just calculated. So look at this one is far, this 394 is far greater than 154. So the generally beam has a very high shear capacity. Generally they don't fail in the shear, so that should be okay. So next step is the serviceability. Now we cannot use the load that we calculated for the strength. Do you remember that we calculated those loads here? 51.6 that we calculated, that is for the strength, that is for the checking for the bending and the shear capacity. We cannot use this 51.6. We need to recalculate this for short term serviceability load, critical load combination, G plus this psi s cube, okay, dead load plus psi s cube. Where this equation coming from? That is close 4.3 on AS 1.70.0 on page number 17. On page number 17, that a combination of actors, page number 17, AS NGNS 1170.2, we have this dead load plus this psi s q live load, and psi s equal to 1.0, that is just one page. On page number 16, we have a floors and others, we have psi value for short term is 1, that we just take it. So that is 1. Substitute the value, that dead load coming from 17.6 that we calculated in the previous steps, 17.6. In the last video we calculate this dead load, and the live load 20.3. Live load we calculated 20.3 in the last video. So substitute this value, and the psi s value 1 give us this 37.7 kilonewton. That's load that is used for the serviceability. Now for simply supported beam with the UDL loads, like here we have simply supported beam and the UDL load. If you want to find the deflections in the UDL load from the structured analysis point of view, we have this 5 WS L to the power 4 on 384 EI, right? That's the coming from structured analysis the value. So 5 times WS is 37.7. Length of the beam is 6000 millimeters, 6 meters, that is given here, divided by 340. This is Young modulus of the steel, that is again coming from the one steel from the Australian standard. That E is coming from page number 40, AS 4100, that is the Young modulus, which is 200 times 10 to the power 3 megapascals. And I for this beam, we selected 360 UB 50.7, so we need to calculate the I for that one. 360 UB 50.7, and the I value for this IX value would be 142 times 10 to the power 6. So that is 142 times 10 to the power 6. I just write this one deflection equation again, that is given 22.4 millimeters. Now we need to check the limit in deflection, delta limit, which is equal to span over 250, that is given on table C1 on page number 27 on AS 1170.0. On page number 27 on table C1, we have this one beam where the line of the side is across sag mid span deflection G plus psi s cube. We have a span over 250, that is taken from the page number 27 on table C1 for the case of beam. So that is span over 250. Span is 6000 millimeters, that is given in our examples. Span of the beam is 6000 millimeters, that is given in our example. Divide by 250 give us 24 millimeters square. So the calculated deflection 22.4 should be less than the limits. That should be okay, because 22.4 is less than 24. So 360 UB 50.7 is adequate beam for the bending. It does not fail in the bending, it does not fail in the shear, and we did the serviceability check for this beam as well, and it satisfy the criteria for the serviceability. So this is the beam that we do in the checking for bending, shear, and serviceability. Thank you.